Hi, my name is Bill Kinney, and this is part 10 of a series that I've been making about parametric curves and the associated parametric equations. We've been focusing on physics application, in particular modeling motion, and recently we've been focused on modeling straight line motion at a non-constant speed. In the last video I introduced you to using grid and plot in Mathematica to try to display graphs side by side and in fact above and below each other to help understand what's going on with parametric curves. In this video we're going to add a couple commands to that, graphics and inset in Mathematica. I will remind you of the programming technique that I showed you in the last video to reduce mistakes. And I will also include a brief discussion about eliminating the parameter, which I've talked about before. It's an algebraic kind of way to verify that we get the same exact line, straight line of motion, even though we're going to be doing it at a non-constant speed. So here is our situation. Once again, I'm not going to restate all this. You might want to pause the video, read that, think about it, draw pictures to understand what's going on. I'm just going to quickly show you the last few things we did in the last video. One thing that I did was I used Mathematica in kind of a neat way. I created a new command that I called paraplot and thought of as a function of b, where b is going to be the animation parameter for the manipulate like I had up here. If that's confusing, watch some old videos. I essentially copied and pasted this code down here, and when I enter this, I have created a new kind of function in Mathematica based on things that I've typed in before that will take numerical input like 0.8 and return a graphical output. Kind of neat. Numerical input, graphical output. This is showing the a snapshot of the motion at time equals 0.8 for our main example from the last video. I also very quickly at the end of the last video did something similar for the x and y coordinate functions. This first function, f of h of t, where h of t was t squared, up here, was giving you the first coordinate of the point as it moves as a function of time, and g of h of t is giving you the second coordinate of the point as a function of time. I made a few changes from the very end. I made a mistake, first of all, in the last video and accidentally put an x there. Now I changed it to a y. That should be a y because this is going to be the y coordinate. I also changed the plot range that I had, and I added this aspect ratio arrow automatic. That's going to make things look nice in the end here. Let me enter these. I also showed you that you can use now manipulate along with grid. I showed you grid in the last one. Here's again the syntax that I'm going to use. B is still going to go from 0.0001, just something barely bigger than 0, up to 1. Grid puts things in a grid, okay? In this case, a square. I'm going to put paraplot of B right there. I'm going to put y plot of B right here, and x plot of B right here. This is going to put the parametric curve in the upper left corner of the grid. This is going to put the y plot, the plot of the second coordinate of the point as a function of time, in the upper right corner of the plot. This is going to put the x plot, the plot of the first coordinate as a function of time, in the lower left corner, and then I have a blank here. Nothing's going to go in the lower right corner. I have a blank after this comma. And it's going to animate it. So we have an animation here. And this is very important. We've got really three functions going on here, remember. We've got the parametric curve here. We've got y as a function of t over here. You see that this is a nonlinear function. And we've got x as a function of t over here. You might wonder, why do these nonlinear functions, they're actually parabolas, why do they produce this straight line here? How can that happen? Well, the technique of eliminating the parameter can help us see why. So I'm going to go back up here and copy and paste what I have here down here. I've got my two original functions, x and y. I've also got my function c. So I'm just cutting out some stuff. That was my original example. In the new example, where you've got non-constant speed, I've also got this other function, h of t equals t squared. And that means ultimately I'm plugging in t squared into all these functions. Making them nonlinear, why does it still produce a straight line then? It does still produce a straight line. Well, use the technique of elimination. What we have here is that in this situation, x equals negative 3 t squared plus 2. Where did I get that? I went to the f equation and replaced t with t squared. That's going to imply that t squared equals, do the algebra, x minus 2 divided by negative 3. And then I don't have to take the square root of both sides. All I have to do here is, in this equation, replace the, once I've got, don't think of it that way. Think of this function here, g of t squared, replace the t squared there with this expression, which will effectively replace the t here with the same expression. Think about that. If that was too fast, go ahead and make that replacement now. Think about this algebra here. Multiply the 4 through the parentheses. You'll get, first of all, negative 4/3 x. Then you'll get negative 2 divided by negative 3 right there is positive 2/3 times 4, that'll be positive 8/3, minus 1, that'll be positive 5/3. And indeed, this is exactly the same linear equation, ultimately, that we got before. Put this in blue here. Showing that no matter what t is, we're still on that straight line. Okay? Just like we got it up here. We used elimination of the parameter before, but now we're doing it in terms of t squared instead of t. But the t squared gets eliminated, and you're left with the linear equation. All right, in the final few minutes here, I want to add a little bit to this last code. I want to add graphics and a key command called Inset to make this output look even better, the output of this code here. This is a bit confusing. In fact, it's confusing for me. It's kind of an example of just do what works, keep experimenting until you get what's going to work. I'm going to put graphics around the xplot. I'm going to put the xplot inside graphics and also inside Inset within the graphics. Inset is a command that's a bit confusing. You can go to the Help menu to try to find out more information about it. Go to the Documentation Center and see some examples and also look at the syntax. And I am basically going to be using this full syntax here. I'm just going to type it first and then try to explain it as best I can. So let's see here. I need a 5, 0.5 in curly braces, comma 5, 0.5, comma automatic, comma 0, comma -1. All right, where did all that come from? Well, let's just see what it produces. Look at this. What's going on here? This is the exact same output before, except what? Look at the lower left corner. It's different. The graph is sideways. Turn your head 90 degrees to the right, and you see you get the graph of x as a function of t when you have your head sideways. What's the benefit of that? Now turn your head back the ordinary way. Look up, down on the left there. The left motion is matching. Just like in the upper right, the upward motion is matching. If you graph x as a function of time sideways using Inset, that's a very nice way to think about the relationship between these three functions. What is all this stuff? That's the confusing part. I had to play with this to try to get it to look nice ahead of time before I showed it to you. If you look at the syntax for Inset, you've got your object here, which is the plot that we got with xplot or xplot of b. You've got position and opposition. These two things are somehow giving you the correct position for this graph. Automatic is sizing it to match what's going on here with the other ones. And this last bit is affecting the rotation. It's going to turn it at this 90-degree angle. You have to experiment with those things to try to get it right, but I did ahead of time, and that's how I got it right. And you would, just to warn you, you need to experiment yourself if you wanted to try to do something like this. And with that, I'll end this video.